So I do want to mention one thing that we haven't talked about, which is interlacing, because if I don't say it, I feel like I will have done it a disservice to the field. And we're not going to go through and do proofs. Most of them rely on Rayleigh-Ritz type arguments and mins of maxes and all these weird things. And so we'll skip that and just sort of state some results, and we'll try to do an application. And I hope we'll succeed in the application. But what's the idea of interlacing? Well, the idea is we have a graph G of some sort. So here's our graph G. And then we do something to it. So maybe we just take a little piece of it out. Like there's this vertex that used to be here, and we've deleted it, as an example of something that we could do. So we might have like G minus a vertex. Or maybe we could talk about G minus just a single edge. Now, once you do something like this, you've changed your graph. And if you change your graph, you may, and usually do, change your eigenvalues. And so there's the question, how are these related? Because the intuition says small changes should lead to small changes. You know, it's kind of like calculus, right? Make a small change, you're not going to go wildly different unless you have some sort of discontinuity. And so the question is, well, does that apply here? And the answer is yes, and that's what interlacing is about. And there's different matrices, and different matrices have different properties. And so let's talk about some of our favorites. And so we'll start with the adjacency matrix. And for the adjacency matrix, we'll compare our graph G, which will have eigenvalues lambda 1 up to lambda n. And I should actually put these in order. So lambda 1 less than or equal to all the way up to lambda n. And then we'll compare it with G minus a vertex V. So this is mu1 all the way up to mu and minus 1. And what happens? Well, if you think about the actual matrices of these, how does the adjacency matrix for our graph G relate to the adjacency matrix for G minus V?
One unit smaller.
So size-wise, it's smaller. What else happens, though? So you have your adjacency matrix for G, and you have the vertex V is indexing a row and a column. What do? Yeah, you delete this row and delete that column, and then life is good. And so in particular, what happens is we end up with a principal submatrix. Now, this is because the adjacency matrix doesn't have to worry about degrees. Most of our other matrices do. And so because you have this very nice principal submatrix, you get the following very nice result, which says, hey, your eigenvalues are going to interlace. So lambda 1 less than or equal to mu 1 less than or equal to lambda 2 less than or equal to mu 2, and so forth all the way down till you get to the end, and mu n minus 1 is less than or equal to lambda n. All right, I did not plan well there, but all right. That's the idea of interlacing. Namely that the eigenvalues, when you delete one vertex, interlace with those that you started with. Now, how do you use interlacing in practice? Well, one of the things that you can do is you can talk about, well, suppose I have a particular assumption on my eigenvalues. And usually we make assumptions about the extreme eigenvalues. And you'll notice that those are the ones that have the most freedom. Because if you think about what happens, if you have interlacing, eigenvalues which are close together are going to end up with more eigenvalues that are close together, right in the same ballpark. It's the ends where things tend to have space and they can move around. So if you put assumptions on your largest and smallest eigenvalues, then that also puts assumptions on any subgraph. Because it says any subgraph also can't have an eigenvalue below your smallest eigenvalue of your big graph, and you can't have any eigenvalue above your biggest eigenvalue. So that leads to saying I can say that certain subgraphs are not permitted. So if I know that I have smaller subgraphs, I have to be careful, I shouldn't call them subgraphs. If I have smaller graphs whose eigenvalues lay outside of the extremes, then I can say definitively, my big graph must avoid it. So interlacing allows you to say you have certain avoidances of substructure. And then once you know that you avoid substructure, that gives you something you can build off of and say, well, since I avoid this, my graph must do that. So this is how interlacing can be used, at least in one way. Now that's the adjacency matrix, but of course, we have other matrices. So let's talk now Laplacian. And this particular topic will apply both to combinatorial and to the signless Laplacian. So combinatorial, that's our d minus a, and then signless is d plus a. Yes?
If we delete a vertex or an edge that results in a non-connected graph,
Right.
is this interlacing still true?
Yes. Yes. And in some sense, adjacency, you can't even tell if a graph is connected or not. That's one of our examples we have. But this is, again, this interlacing result is particular to adjacency. So you'll notice that we make careful assumptions about what kind of matrix we're dealing with. Because adjacency matrices will behave different than Laplacian, will behave different than normalized Laplacian, and so forth and so on. So you have to make sure you're in your right setting. Now, what happens for our combinatorial, our signless Laplacian? Well, here, we don't want to talk about deleting a vertex. And deleting a vertex is tricky because, again, I mentioned this already, but if you delete a vertex, that deletes edges, which, of course, were connected to other vertices, which affects degrees. And so it has a propagating type effect. So for the Laplacian, what you look at is you look at G, and let's see, how are we doing with our Greek letters? All right, should we? We use alpha. Alpha 1 less than or equal to alpha 2, all the way up to alpha n. And then we'll look at G minus an edge. So we're deleting an edge. And now, what do we have? Well, we have beta 1 less than or equal to beta 2 less than or equal to all the way up. So, all right, good. Well, what's our conclusion? Well, our conclusion is that alpha 1 is less than or equal to beta 1, which is less than or equal to alpha 2, which is, so I have to make sure I have these in the right order. Well, according to this, yeah. Oh, wait, no. I have to, let me say it this way. Beta 1 is less than or equal to alpha 1. There we go. Less than or equal to beta 2. Less than or equal to alpha 2. And all the way through. Now, okay. You'll notice here that in general, that we have that beta I is less than or equal to alpha I and greater than or equal to alpha I plus 1. Alpha I minus 1. I know how addition and subtraction works. And so more or less, what are we learning? Well, when we delete an edge, what should happen to our eigenvalues? Because alpha was the one where we kept the edge, and beta was the one where we took out the edge. Our eigenvalues are doing what? They go down. So all our eigenvalues drift down. All of them do. Now, of course, you have to put this in quotes, drift down, because they could maintain equality. But this is not a case where when you delete an edge, eigenvalues might go up. Because you can actually have that happen for the adjacency matrix, where you delete an edge, eigenvalue, a particular eigenvalue goes up. Now, another way to think about this, if you delete an edge, your eigenvalues drift down. You can also say, well, if I add an edge, my eigenvalues drift up. And so we get back to our discussion, at least our mention, that we're interested in our small eigenvalues, and in particular for the Laplacian, your first eigenvalue, not interesting, 0. Your second eigenvalue, and your second eigenvalue being your alpha 2, that's the interesting eigenvalue. That's called algebraic connectivity. So every time you add an edge, that eigenvalue should go up. And it's measuring how connected you are. And roughly speaking, we've said this before, a small value of alpha 2, poorly connected. A large value of alpha 2, well connected. And that's just, well, an intuitive idea. Now, why might we do it this way? Well, if you think about what we had before, we talked about, we had principal submatrix. When we delete an edge, we don't have a principal submatrix. So how might we get from G to G minus C? Well, you can remember that one way we formed L was through signed incidence matrices. And so, when we're talking about deleting an edge, what's the effect? Well, you take your signed incidence matrix and you delete the corresponding column or row, depending upon if you're looking at the matrix or its transpose, and then carry out the multiplication. And so roughly speaking, it's because of this structure that we get the interlacing that we do. All right, well, we have space. Normalized Laplacian. Okay. And what happens there? Does it behave like adjacency, or does it behave like Laplacian? Yes?
Maybe I'm trying to see like where we delete a row. Like it's clear that we delete a row in one matrix and a column in the other one.
Right.
But shouldn't it, like, as far as my understanding goes, is that the incident matrix is vertices, number of vertices times number of edges. So shouldn't it be like a row here and a column the other one?
Well, so it depends on
Oh, but we're taking edge
right.
and edge. Oh.
So the vertices, edges, so deleting an edge.
I don't know why my head was thinking again of deleting a vertex. So it will be the opposite if we were deleting a vertex.
Right. If you're deleting a vertex, it'd be the opposite, yes. Now, for the normalized Laplacian, it is very similar to the Laplacian. So we're going to look at G, and all right, let's see, where are we in our alphabet? I guess we'll go with the gammas. You have gamma 1 all the way up to gamma n, and you look at G minus an edge, and that's delta 1 all the way up to delta n. And now, what happens? Well, you get the following. You get that delta I minus 1 is less than or equal to gamma I is less than or equal to delta I plus 1. And so it is slightly different when you compare, because you'll notice here that when you deleted, things tended to drift down, but that's because you have alpha I versus beta I. Well, now it's not exactly gamma I and delta I. So it has the ability to wiggle. So there's a little bit of wiggling that goes on. And on a subnote, you can talk about, well, what if I delete a series of edges? Is it better to delete them one at a time, or like a Band-Aid, rip it off all at once? And the answer is Band-Aid. It's better to rip things off all at once. And that was one of the things that I did when I was a grad student. But, all right, now one interlacing result we'll talk about. So these are some. And I want to talk about a nice result. And one person who wrote a wonderful survey paper, his name is Willem Hamers. I think he's retired now. Yes? I'm sorry.
Sorry, I have a question about your last slide.
Sure.
Do you mean like there's less change if you remove all the edges at once and not?
Well, so yes. What do I mean by better? That's a good question, because I didn't specify what I mean by better. So if you think about removing edges one at a time, then what you get is you say, okay, well, how many edges did you remove? And that says you how far you have to look. So you have to say, well, if I remove 10 edges, 10 edges is actually a good number, good. I like 10. All right, if I remove 10 edges, well, I could wiggle up to 10 of my eigenvalues, steps of the eigenvalues in both directions. But what happens if the edges you remove are clustered together? So let's say they form a K5. Then what you can do is you can say, well, I actually just have to say how many vertices were involved, and I think you have to add 1. Or maybe subtract 1. Subtract 1. So now, instead of looking 10 in each direction, you look 4 in each direction. And so there's less wiggling going on. And so the justification is to say, if what you're deleting is interacting with each other, oftentimes you can be a little bit more compact in saying how much things move. So that's why I say it's easier to, if you're going to remove things, remove them all at once. And that way you don't have things compounding. All right. Well, so here's an interlacing result. And this is just a very generic thing about matrices. So we'll say A is n by n. We'll keep things real symmetric. And the eigenvalues are lambda 1 greater than or equal to lambda 2 down the way to lambda n. And then S is an n by m matrix with S transpose S equal to the identity. So the idea here is, if I think n by m, let's see, what's the nice dimension? So So I multiply, and I get out an identity matrix. So it's not saying that S is invertible, because it's the wrong shape. But it's almost like it's saying that. So it's almost like oh, it's kind of like we're going to do some sort of similarity type thing. But what's going to happen is we're going to shrink down. So in our particular case, we're going to look at B, which is S transposed AS. And now what happens when we look at our sizes, this is going to be an M by M matrix, and it's real symmetric since the center is real symmetric, and we'll assume S is real. And, sorry about that. And this has eigenvalues mu1 greater than or equal to mu2 all the way down to mu_m. Now, the conclusion, these are all our assumptions, is then we have that lambda I is greater than or equal to mu I is greater than or equal to lambda n minus m plus I. And a lot of the interlacing results can basically follow from this by making a very good choice for S. So we're going to make a very good choice for S in a moment. Okay. So now for something that looks very different. Chi of G. Do we have any graph theory fans in the audience today? What is chi of G? Yes, the chromatic number. Good. All right. So the chromatic number of a graph. Well, what does that mean? It means I get to take advantage of having colored pens. That's what it means. So you start with a graph, and the goal is you color. So how does one color? Well, each vertex gets assigned a certain color. And then there's this notion of a proper coloring. What makes a coloring proper?
Is that just like the fancy name for none of the edges and edges of the same color?
Yeah, so no two adjacent vertices have the same color. So for example, if I color this corner, well, I should say this vertex, a yellowy color, then I can't color any of its neighbors yellow. But I could color, say, this one over here yellow. And then I'd say, well, okay, now I have to do something more bleu. So here's a blue one. And I can make this a blue one, I can make this a blue one. And finally, rounding it out, we'll put a red one here. All right, so there we go. There's a successful coloring of this graph. We were somehow able to do it with 3 colors. Amazing. Amazing. To be honest, this graph is not hard to color with 3 colors. That is true. That is true. Now, how do we think of coloring? So oftentimes when we think about this problem, we say, oh, this is all about, putting colors and life is good. But really what colorings are is something slightly different. So the goal is, what do we do when we do a coloring? Well, we're really decomposing our vertices into independent sets. So that's what colorings ultimately are. So, for instance, everything that we colored with our yellow color, we could call that the first group. The blue color we can call our second group, and the red color is our third group. So we've taken our vertices and now split them into 3 groups. In each group, they have to be an independent set. And of course, we should say that out loud. Why are they in an independent set? Yeah, because we can't have any edges between things of the same color. Exactly. Say, okay, great. So graph coloring problems are really ultimately about decomposing vertices into independent sets. It's usually not phrased that way, but it's true. Now, how does this translate into the adjacency matrix? So let's suppose we've got a coloring. We use our coloring to label. So we have our collection of independent sets, so we put maybe the yellow group first, then the bluish group, then the red group, or however many colors we have. We might have to come up with like some really creative names for colors. Vermilion, chartreuse, whatever it needs to get down there. One of the few memories I have as a child, this has nothing to do with spectral graph theory, but now you can be like, so that's why Steve is broken that way. But one of the few memories I have as a child was we were playing a guessing game where the instructor sat at the front, said, I'm thinking of a color. The first person to guess my color gets to have this really cool pencil. It was a cool pencil, so we wanted it. And there were about 20 kids, and it took like 70 guesses because they went through it and then through it and nobody guessed. I think it was green. Well, the problem was people first, they guessed a few of the obvious colors, and they also know, so they started guessing weird colors, and then they kept staying with weird colors. And I won, by the way. I just want to be clear about this. I won. That's why I remember it. The people who didn't get the pencil have no memory of this event, but I do.
Do you still have it?
No, it wasn't that cool. In retrospect.
Okay.
But my great secret was, after about halfway through, I said, I'm just going to pay attention to what people are guessing, and what colors aren't they guessing? And that was like a brilliant insight to me when I was a young kid. It's like, oh, I can use that information. Okay, so in terms of the graph, what happens? Well, let's say we have 3 colors. Roughly speaking, we can put into a block structure. What can you say about these blocks? Right. You got 0 blocks on the diagonal, and then you have stuff here. Now, when we say stuff, there could be some 0 entries, but we don't know. But what we know definitively is that we've got these 0 blocks. And now we're like, oh, if you squint your eyes, it kind of looks like a smaller matrix with zeros on the diagonal and then other stuff on the off diagonal. And could we use that? Could we do that? And the answer is going to be yes, we can. Okay, so this is our original matrix A. And what we want to do is we somehow want to compress this into some smaller matrix B, which really is just in this case, a 3 by 3. That somehow keeps useful information. Okay, so that's our goal. Now, we have to decide what do we want to keep. And so, what will we do? We want to find an S, so that B is S transpose to AS. Okay, that's great. So we want B equals S transpose to AS. We want S transpose to S to be the identity. And we say we want one more thing. We want to have that lambda 1 is an eigenvalue of B. Okay, so that's our goal.
And lambda 1 was an eigenvalue of
A. Okay. Yeah, so lambda 1 is our largest eigenvalue. So oftentimes we care about the big ones. Yeah, the small ones, whatever. But the big ones, we want those big ones. Okay, well, cool. We can do that. We have technology. So, since we're after lambda 1 being an eigenvalue, we know that there's an eigenvector. So let's say that x1 is an eigenvector for lambda 1. And so that says when we multiply our a by our x1, we get lambda 1 x1. And now, this should come as sort of no surprise, say, well, hey, since we have this block structure that we're using for A, let's use that to split up our x1. And so what we'll have here, well, we'll call it, say, x1, piece 1, x1, piece 2, x1, piece 3. And I'm sorry, I'm writing very small and hard to read, but the idea here, I'll blow it up. So we have x1, piece 1, all the way down to x1, and then the last piece is, the number of pieces we'll point out is the chromatic number. So in this case, 3, but it could be 7, could be 2. All right, so do we know anything about this eigenvector, or can we make some assumptions about this eigenvector? And let's go ahead and just assume in the background, let's assume G connected, just to simplify our conversation. It turns out for chromatic number, it's easy to do chromatic number of components. You just take the chromatic number of each individual component and then take the largest, take the max. So, thinking back to what we've talked about this semester, maybe not necessarily have proven, but have used it. Given that we have the eigenvector for the largest eigenvalue, what are things that we can assume about the eigenvector for the largest eigenvalue?
I feel like it's the all ones vector. Or it's the
Well, the all ones would be if it was regular.
Okay. It's all positive?
Yeah, it's all positive. And why is that? That's all right. Peron Frobenius.
Yeah.
And so that's what gives us, that we have all positive. Okay, so.
One of those things that it's like muscle memory, just assume it.
Right. It's just, exactly, that is what we do. That is precisely what we do. Okay, so I want to make sure I have this handy. Now remember, our goal is to form an S. So we say, okay, so we have this eigenvector, which we can partition. So here's our idea. What we're going to do is we're going to form sort of a stepping stone. We'll call it S hat. And the way you form S hat is in the first piece, you just grab the first entry and then you make the other entries 0. That's your first column. The second column, you grab the second portion of it, and then the other parts will be 0. So when I write zeros, it's not a 0 number, it's a list of zeros, because we're making columns. And then the third will be similar. So as we're taking our eigenvector, and we're basically pulling it apart according to the block structure. So the portion of the eigenvector for the first block goes in the first column. Portion of the eigenvector for the second block goes in the second column. So forth and so on. All right? Now, is this our S? Probably not. Why not? Because it has a hat on it. Grrr! Okay. All right. So what's our problem? Well, when you take our S hat transpose S hat, these columns are orthogonal. So the good news is off-diagonal entries are already 0. Cool. What about the diagonal entries?
The norm is square.
Yeah, so it's like you're taking the first vector and dividing it with itself,
Yeah.
which is the norm squared. It's a number. So we'll give it a number name. We'll call it, say, F1, F2, F3, so forth and so on. In general, where Fi is, as you said, the norm of the ith piece, 2 norm squared. All right, well, that would be cool if that was the identity, but it doesn't have to be. There's nothing that requires that these numbers are all 1. But because we know that these entries are all positive, these numbers are all positive. So let's give this matrix here a name. We'll call it capital F. And we'll let our matrix S be equal to S hat and then capital F to the minus a half. Much like we've talked about degree to the minus a half. Okay, now, is this an S we can use for our interlacing result? In other words, do we have S transpose S equal I? Well, do the computation. Okay, so here we go. We'll slide this up and bring it back when we need it. So check 1. S transpose S. So taking this, we have, that would be F to the minus a half. Notice F is symmetric. F to the minus a half is symmetric. S hat transposed. So that's our S transposed. And then S is S hat and F minus a half. But, this is F to the minus a half, F to the minus a half, which is the identity. All right, good. So we can definitely now use this S and make a B. But we said there's another thing we wanted. We want lambda 1 to be an eigenvalue of B. Okay, well, now we have to figure out, is lambda 1 an eigenvalue of B? So, that's check 2. Okay, so I guess we should point out check 1 was, does S transpose S equal the identity? Check 2, lambda 1, an eigenvalue of B. And, well, all we have to do is produce an eigenvector. And so here's one I claim works. Let Z equal F to the positive 1/2, and then all 1s. Now, this feels kind of like things that we did for normalized Laplacian. Yes. Because we talked about things like harmonic eigenvectors. So, when I talk about the all 1s here, this is the smaller size. So I want to check what happens when we take B times Z. Are we going to be happy? Well, hopefully. We'll do a little bit of BZ work, and we'll get something that we like at the end. Yes? Yeah? You don't like the BZ work?
It was a bad joke.
I thought it was brilliant. You're hurting my feelings. But that's okay. That's all right. All right, so we remember what B is, S transpose AS. Okay, so we have our S transpose. Actually, we can just copy it from up here. That's F to the minus a half S hat transpose. Then we have our A, and then we have our S hat F to the minus a hat. And so there's our B matrix. And times F to the 1/2 all ones. All right, well, a couple things are easy to spot. Namely, F to the minus a half times F to the 1/2. They cancel each other. Now, what happens? We're taking S hat, we're timesing it by all ones. And if you think about what does that mean, it really means when you take a matrix times a vector, you're adding into the columns. And in particular, it says add 1 times the first column, plus 1 times the second column, plus 1 times the third column, and so forth and so on. So when you put these two together, what comes out is our x1. It's the eigenvector x1. So we have F to minus a half, S hat transposed A, x1. But what do we know about x1?
Eigenvector A.
Yeah, it's the eigenvector for A, for lambda 1. So this becomes lambda 1, F minus a half, S hat transposed, x1. Now, we say, okay, great. Well, what goes on here? So we're taking S hat transposed, which is this matrix, and we're timesing it by x1. And so, how are we doing on time? Okay, we're going to go just a little bit over. So what's going to happen is when you go at the transpose, S hat transpose, well, it's the first part transpose, and then it's a bunch of zeros. Then it's the second part transpose and a bunch of zeros, and so forth and so on. So when you multiply it by x1, what comes? Well, you're going to get the x1, the first part of it, the norm squared. x1, the second part, norm squared. x1, third part, norm squared. In other words, this part right here is equal to what we've been calling F times all 1. So this is lambda 1, F minus a half, F all 1s. Well, F to the minus a half times F, that's F to the half. So that's F to the half times all 1s, which is Z. All right. So we now have verified our 2 checks. Good. And we have almost no time left, but that's all we need to finish our great aha. We now know that our matrix B has lambda 1 as eigenvalue. It's because we verified that. What's the sum of the eigenvalues of B? Let's say we call these mu i's. So sum of the mu i's. It's the trace of B, which is? So by design, what does B have on the diagonal? 0. All right. Now, what's true about mu2 all the way up to mu chi of G? Well, these are all eigenvalues of B. eigenvalues of B interlace eigenvalues of A. So these all have to be greater than or equal to the smallest eigenvalue of A, which is lambda n. Yes? Okay, so here we go. We now have that the sum of the eigenvalues is 0, which equals lambda 1 plus mu 2 all the way to mu chromatic number of G. That's the size of our matrix, is the chromatic number. Well, that has to be greater than or equal to lambda 1 plus lambda n plus all the way down to lambda n. And here this is chi of G minus 1 times. So that's lambda 1 plus chi of G minus 1 times lambda n. Now what can we do? We can solve for chi of G. So, oops, I've got my lambda 1. You move the lambda 1 across, divide by lambda n, add 1 to both sides, and you come to the conclusion that the chromatic number has to be at least as large as 1 minus lambda 1 over lambda n. So knowing the eigenvalues gives you a lower bound for your chromatic number. Now, you might be a little bit skeptical about my ability to divide, saying, Steve, you got your inequality in the wrong direction. Shouldn't that be a less than or equal to? And the answer is no, it should be a greater than or equal to, because there's a small, subtle thing. What's true about this lambda n that we divide by? It's negative. And when you divide by negative, you have to flip the sign. So that's why it feels wrong, but I promise you this is the correct thing. How good is this? Well, let's pick a family of graphs that we know. Bipartite graphs. What's true about bipartite graphs?
They're too colorable.
They are too colorable, that's true. What about the eigenvalues for the adjacency? Yeah, so in terms of lambda 1 and lambda n, they're equal in magnitude, they differ in sign, which means that lambda 1 over lambda n is negative 1. Yeah. And so we come to the conclusion that for bipartite graphs, the chromatic number is at least 2. So now we have a proof that bipartite graphs need at least 2. It doesn't prove that you need exactly 2, but it proves you have at least 2. This is by no means tight, but it works pretty well for a number of graphs. And it shows you what you can do with a good set of tools. So, all right, that's our final lecture. I know we didn't cover every possible topic in spectral graph theory, but I think we covered a lot of fun things.